What does it mean for a line to be tangent to a curve at a particular point? Well, when we first learned about the word tangent, it was back in geometry and it was associated with circles. Like we can see in the picture on the left-hand side, we got a black circle. We have this pink line here, and this pink line is tangent to the circle at this point because it touches the graph once. Right? And if we go back to that Latin word, it just means touching, and it touches specifically at one point. That's what a tangent line meant. Now, also in geometry, I have this theorem which says that a tangent line is perpendicular to its radius at that particular point. Useful theorem, but not really part of the definition. So, unfortunately, that definition isn't enough in order to define a tangent line to some kind of curve that's not a circle. So on the right-hand side, we have this function, this black function c here, and we have two lines that intersect at point P. We have this pink line T, and we have this blue line L. Which of those two lines is a tangent line to the curve at point P? Well, if we use the exact same definition that we used from geometry, then the line that we would think is tangent is the blue one here because it touches at just a single point. Unfortunately, it's not. It's the pink one, which is weird because this pink line touches not just at one point, but it touches at 2 points, right? It touches over here. I'll even label that point. Maybe we call that point B. Now further, not only is the pink line a tangent line, but it's only tangent to the graph at P. It's not tangent to the graph over here at point B. So what's the difference? What's the difference between these 2 points? Why is it tangent over here and why is it not tangent over here? And furthermore, like, why isn't the blue line tangent at all? So what do you suppose the graph would start to look like as we really zoomed in at this point P versus this one right here at B? Which one of those graphs, the pink one or the blue one, would it start to look more and more like? Here, let's take a look over here at Desmos, at this idea. So here is good old sine x, and what I have graphed also in red is a tangent line, this dashed line here, and I can move it around. It's like a roller coaster. Okay. Now, as we said, we can't just simply say that a tangent line touches a graph at just one point, because as it is situated right now, it's touching at 2 points, right? But it's still tangent at point P. And what I also mentioned is, like, what do you think the graph looks like as we start to zoom in at that point P? I'm going to zoom in closer and closer and observe what is happening. You can see that the graph is starting to look more and more like that tangent line, right? And what was that called? What's that called again? I think that's called local linearity. And that's what makes this one in particular the tangent line. If I come back over here to the slideshow, it's what rules out the blue line. If I were to zoom in on the graph at that point, it's not going to look like the blue line. It's going to look like the pink one. Same thing is going to be true over here at this point P. So the way that we're going to state this, at least informally right now, is that a line's going to be tangent to a curve at point P if it intersects the curve at point P and has the same direction as the curve around that particular point. And direction, at least for lines, it's kind of associated with slope, right? If I knew that a slope was positive versus negative, I would know which direction it was pointing in. Okay, so the idea behind a tangent line, now this particular tangent line, it does touch the graph at 2 particular points, but I wouldn't know this point B further down the line. Let's say I wanted to find the slope of that line. I want to find the slope of this pink line, the tangent line, because it's associated with the slope of the curve right there. I have a problem because the only coordinate I would actually know is point P. And this is what's known as the tangent line problem. It's a classic problem that led to the development of the first kind of calculus, which is called differential calculus, tangent line problem. Tangent line problem is simply this. I want to find the slope of a tangent line, but I only have 1 point. Yes, it is entirely possible that a given tangent line intersects the curve at more than 1 point, but I wouldn't necessarily know the coordinates of that second point, right? So how am I supposed to tackle this? I cannot find the slope using just a single point. What's needed is a second point, which makes this thing called a secant line. So a secant line touches at 2 points, specifically over some sort of interval, and it's taken from a Latin word secans, which means cutting. So it cuts across. That's also associated with circles. So back in geometry, when we defined a secant line, it was a line that intersected a circle twice. Now this line, this blue line here, I can find the slope of it because it has 2 points. I can find the slope between 2 points. So really what I want, let me come back over here, I want the slope of the line only through x comma f of x. But I don't have enough information. So what I do, what mathematicians came up with, is selecting a second point, maybe a point that's just further to the right, just a little bit. We're going to call that thing h. Sometimes it's called delta x. We're just going to march to the right by some small amount, and I'm going to find a second point on the curve. So this point is called x plus h. I've added something to it. Maybe it's 1 or something smaller than that. I plug it into the function, and I get its y coordinate as f of x plus h. So those are 2 points that are on this graph, and I should be able to calculate the slope between those 2 points. And that's what I would like for you to tackle here. So try to, in terms of x, h, and f of x, try to find the slope between those 2 points, the slope of that secant line. And then we will come together, see if you got it right in the next video.